Hello everyone, and welcome to CRAMSURG, Clinical Research Appraisal and Methodology for Surgical Trainees, where we pick a paper fresh from the press on a hot general surgical topic. We review it for you, we present it for you, we critique its methodology for you, and provide top-of-the-field expert opinion and teaching on research appraisal and methodology. My name is Gio Perrin, and together with Professor Sababala Subramanian and Maria Digby, we bring you CRAMSURG from the wonderful region of the Yorkshire and the Humber.
Let's get straight into it. We continue our statistical tests, how to guide series of presentations. Today we're going to talk about Pearson's correlation. Usual disclaimer, not a statistician, not an expert in stat software. Feel free to ask any questions. If I don't know the answer, I will look it up and clarify. So far, we have talked about assumptions, and we talked about assumptions again and again and again, because they're very important. We talked about students T, ANOVA, wedge ANOVA, two-way ANOVA, per sample t-test, repeated observations ANOVA, and we also looked at how to run them. Today, we're going to move forward. We are going to remain on continuous data. We're still looking at normally distributed data. And we're going to talk about the concept of correlation and what it is mathematically, as well as how to run it on Jamovi, which is our favorite software. So let's start with the person who sort of didn't necessarily create the concept of correlation, but certainly made it popular to the point that the correlation coefficient is known as Pearson's correlation. Very famous statistician. He fathered Biometrica, which used to be the most important statistical journal in the world. If you remember, that's the journal where the student's t-test was published by Mr. Gossett. He was also a mentor of Sister Florence Nightingale, that you can see in the picture there to the right at UCL. His sort of main legacy was basically creating this massive observatory of data where, for example, people would come in to register their own height and weight and the height and weight of their children. And Pearson was trying to figure out a relationship between the two, and he came up with the concept of regression to the mean, for example. So very, very important person. Of note, he's reported in the vast majority of his papers as K. Pearson, but his original name was actually Carl Pearson with a C. He changed his initials from C to K in honor of Karl Marx. So let's go to correlation. What is correlation? Well, correlation is a measure of statistical relationship between two variables. And if you want to be boring and express it mathematically, which I feel we should do to an extent, is the ratio between the covariance of the two variables that you're looking at and product of their standard deviations. Now, we all know what standard deviation is because we talked about it in previous lectures. Let's briefly touch on covariance, again, without getting too boring. Covariance is a measure of how two variables change together. Or joint variability. It's basically a result of the difference between the value that you're registering and the mean of that particular distribution, and they are considered together for the two variables that you're looking at. In order to understand variance and standard deviation, I'll refer you back to chapters 13, 14, and 15 that you can find on our website, and they will give you a detailed breakdown of variables and measures of our distribution is including variance and standard deviation. So the correlation coefficient is the jump forward. So we talked about correlation as a concept. We now are talking about how to express that numerically. And basically, if you plot the two variables together, you can find out that they can be very much positively correlated or negatively correlated or not correlated at all. And there is a whole range that goes from 1 to -1. And this is because, again, this is the result of a ratio. So basically, it can only range from 1 to -1. The strength of the correlation is then again measured on a numerical scale. Most commonly, it is also accompanied by a p-value, which will tell you how statistically significant that correlation is. Assumptions are important here as well. We still need to check for normality, and to an extent, particularly Pearson's correlation is also sensitive to scarcity, although not as much. There is also another very important variable to remember, which is independence. The two variables that you're looking at have to be independent from each other, so you can't run it, for example, on repeated measures. Now, if there is one thing that you need to remember from this lecture, is that correlation and causation are not the same thing. Now, I don't know how many of you are familiar with a satirical religion called flying spaghetti monsterism or Pastafarianism. It was described the first time in 2005 by a guy named Bobby Henderson, when the Kansas State Board of Education decided to allow for the teaching of intelligent design, which is basically a theory whereby God has created all creatures at one point, as an alternative to evolution in schools. This quite upset Bobby, so he decided to write a letter to the Board of Education highlighting how he thought his own theory on creation, which obviously relates to the flying spaghetti monster, should be taught in school. And as part of his religious rant, he described also a very key concept in flying spaghetti monsterism, which is the obvious causative relationship between the declining number of pirates in the world and the raising global average temperatures, which, as you can see in this chart, that demonstrate correlation. You know, it's very obvious. The pirates are disappearing, so the temperatures are going up. Obviously, it was taking the proverbial P. This is purely a matter of correlation, not a matter of causation. So it is very important to remember that correlation and causation are two very different things. Okay. And again, this is probably the only important thing that you need to remember from this. Now, as usual, let's go into an example. And let's go back to my lovely dissertation data set. If you remember, I collected data about papers that were advertised on the Twitter network by publishing journals. For the purposes of today's example, I collected data on retweets and likes. Are these two variables correlated with each other? Well, we'll soon find out because we're going to have a go now. So let's load our data set. Which you will probably now remember from the previous lectures. We will find the correlation matrices under the level regression on Jamovi for some reason. You just click on correlation matrix. You can choose which type of correlation coefficient you want to know about. For the purposes of today's example, we'll pick Pearson. Next time, maybe we'll talk about Spearman and what it means. And let's look at retweets, and let's look at likes. And as you can see, there is a correlation, which is quite strong, 0.964. This is a positive correlation. So as the retweets grow, the likes seems to grow as well. There is also a statistically significant p-value. You can also ask Jamovi for a correlation matrix, and it will show you a chart with the two variables and obviously the line in the middle. You can also choose a hypothesis, so correlation or positive correlation or negative correlation if you want. And you can ask for confidence intervals. You can't check straight here for assumptions, so you will have to go on your exploration if you want to check if retweets and likes are normally distributed, and go on descriptives and run your Sheffield-Wilk test, for example. Right. I think we'll call it for today.
Thank you everyone for tuning in and listening. Until next time, keep ramming your life with our surgical podcast.